dear students, welcome to IMS Academy. My name is Vipin Mishra and I welcome you all in this smart revision series of IMS Academy. And this is going to be the part 4 of the revision of subject power electronics. So we already completed part 1, 2 and 3. In part 1 we discussed power semiconductor devices, in part 2 we discussed DC to DC converter, and in part 3 we discussed the inverters. And this is going to be the last lecture in which we are going to just revise very quickly this chapter rectifiers. Now this chapter has a lot of formulas, okay. So let's have a revision of rectifiers. So when it comes to the important topics are single phase rectifier, three phase rectifiers, and the most important topic nowadays is fact of source inductance. Regularly we are getting questions from this particular topic, okay. So let's get started with the classification. So before I start, let me tell you few things. So we have something here which is called as the pulse length, okay. So what is this pulse length? So the pulse length has a formula 2 pi over m, okay, provided that m cannot be equal to 1 and it can have any value, okay. Then we have another important formula for output frequency. These two are the important terms, output frequency. The output frequency f naught, this is given by m times fs, which is where fs is the input frequency, okay. Now what is this m? So m is basically nothing but the pulse number, okay. So m is the pulse number, okay. As the pulse number increases, as the value of m increases, what will happen? The output frequency increases, and as the pulse number will increase, the ripple content will decrease, okay. The ripple content will be decreasing and we are moving towards more perfect DC voltage, okay. So as per these formulas we can divide our converters into single pulse converter. So when it comes to single pulse converter, so in single pulse converter what will be the pulse width? So the pulse width will be 2 pi, okay. The pulse width for single pulse converter will be 2 pi, and when it comes to two pulse converter, what will be the pulse width? The pulse width will be 2 pi over 2, okay. Now we will be using this formula. 2 pulse converter means m value is 2, so 2 pi by 2, that is what will be the pulse width? It will be pi, okay. What will be the output frequency? So the output frequency here will be equals to fs, okay, and output frequency here it will be f naught equals to 2fs. Similarly we will be having 3 pulse converter, okay, 3 phase rectifier. This is single phase half wave rectifier, this is single phase full wave rectifier, this is 3 phase half wave rectifier. So in 3 phase half wave rectifier, what will be the pulse width? So the pulse width will be 2 pi over 3, okay, or 120 degree. And what will be the output frequency? So the output frequency, that will be equals to 3 times fs. Now we will be having 6 pulse converter as well. So in 6 pulse converter, what is the pulse width? The pulse width will be 2 pi over 6, okay, or we will be getting pi by 3 or 60 degree will be the pulse width. And what will be the output frequency? So the output frequency here will be 6 times fs. So we will be getting 3 pulses for a complete 2 pi cycle here, we will be getting 6 pulses for a complete 2 pi cycle here in this converter. So this is how, based upon the pulse width and output frequency, we can classify different converters, okay. This is how we can classify them. Now analysis on DC side of converter. So in rectifier we have AC side and we have DC side, okay. So AC side, good afternoon sir. So in AC side, AC will be available, and in DC side we have controlled DC, okay, or uncontrolled DC, depending upon whether we are using diode or the SCRs. Now what will happen during the rectification operation? There will be harmonics that will travel both at the source side and will be at the load side as well. Source side is AC. When they are going to source side, they are just corrupting the source power quality, okay. So AC will be corrupted, or it will be having bad power quality, non-sinusoidal AC currents and voltage you may get. When it comes to DC side, when it comes to DC side, what will happen? We want to have perfect DC, but those harmonics will travel into the DC side as well, okay? And when they will go to DC side, we will be having corrupted DC as well. So DC power quality will not be good, okay? Hello. So what will happen? We will be having disturbed DC side as well, okay? So when it comes to DC side, in order to calculate, in order to measure the effect of these harmonics, we will be calculating something called as the form factor. Okay, we will be calculating something which is called as form factor, and this will be equals to the RMS output voltage divided by the average output voltage. Okay, and then we will be calculating something called as voltage ripple factor. Voltage ripple factor VRF. This will be under root of form factor square minus 1. Okay, form factor square, yes, very good Nilmesh. So we will be having voltage ripple factor and form factor. Okay, and for perfect DC, what should be their value? So for a perfect DC, the form factor, it should have a value equal to 1, and there should not be any voltage ripple factor kind of thing. Okay, but if it is not a perfect DC, you will be getting form factor greater than 1 and voltage ripple factor will be having some value. Okay, so this is the analysis that we will do at the DC side of converter. Now harmonics will travel into the AC side as well, and there we will be calculating few terms. Those are called as current distortion factor. Okay, current distortion factor. Now you are giving sinusoidal AC voltage, but due to the harmonics, the current at the input side, it has multiple frequency terms. Okay, so it no more remains a sinusoidal current, but in fact it is having harmonics as well. Okay, so we will be calculating current distortion factor, which is called as CDF, and that will be equals to the fundamental component of current, its RMS value you will take, divided by the total current RMS value. Okay, and let me write it source current because we are talking about source. Okay, so fundamental source RMS current divided by the total RMS value of the source current. That will be the current distortion factor, and then we will measure something called as total harmonic distortion. Okay, then we will measure something called as total harmonic distortion or THD. Okay, so total harmonic distortion or THD, this is equals to under root of 1 by CDF square minus 1. Okay, now again when it comes to perfect AC, what will be the value of CDF? CDF should be equal to 1, and when it comes to THD, it should be equal to 0, no harmonic distortion. But if it is a distorted AC, CDF will be having a value less than 1 and THD will be having very high value. As per IEEE standard, 5% harmonics are allowed. Okay, but ideally there should not be any harmonics. Okay, so this is what we have. Now single pulse converter, so single phase half wave converter. So this is single phase half wave converter excited by AC, and we have this switch thyristor. This is the load. We may or may not use the freewheeling diode. Okay, so it depends upon the load. If suppose the load is having inductor, then the freewheeling diode will be coming into play. Okay, so let us consider that first of all we have R load or we have RL load with freewheeling diode. So if we talk about these loads, what could be the output voltage average value? So for these loads, the output voltage average value will be Vm by 2 pi 1 plus cos alpha. This becomes a very important formula for us. Okay, Vm by 2 pi 1 plus cos alpha. In all the half wave converter, the pulse, the time period will be 2 pi. Then if you have to calculate I naught average, you can calculate I naught average simply by V naught average divided by R. Okay, because average voltage across the inductor is 0. Then if you have to calculate the RMS value, okay, So for RMS value we have a formula. Okay, so how to calculate the RMS value? So for RMS value, what you will be doing, you will be writing Vm over under root 2 into time period, and then you will write high limit minus low limit, and then you will write 1 by 2 sine 2 alpha, and then you will put lower limit first, and then you will put higher limit whole to the power 1 by 2. Okay, so that formula you must be using to calculate the RMS value, and through this formula you can calculate the RMS value, because we know the limits and time period. So time period is 1 by 2 pi, and here you will be getting the output voltage from alpha to pi, and you have Vm sin omega t d omega t. Okay, so just by putting the limits, if you know the if you know this particular formula, you can calculate the RMS value if it is required. Okay, then if you want to calculate the power factor, then you have to equate the input power and the output power, and finally what you will be getting is V naught RMS divided by the source RMS, and that is something that will be used to calculate the power factor. Okay, so when we have R load or RL load with freewheeling diode, these are the important formulas. Fine, I hope it is clear to everyone. Then if suppose we have RL load, okay, so if suppose we have RL load, in case of RL load, the output voltage formula, it will be the average output voltage, it will be equals to Vm by 2 pi cos of alpha minus cos of beta. Okay, where what is beta here? Beta is the extinction angle. Extinction angle. Okay, so after pi there starts the negative cycle, half sine 2 omega t. Okay, I have written something else. Yes, y2 alpha will come, it will be 2 omega t. Thank you so much. Sine 2 omega t. Okay, just a correction, here you have to write 2 omega t because no alpha has come into play. Now you will put the limits as per the integral. Okay, so what is this extinction angle? After pi there starts a negative cycle, so switches must be off. But what will happen? Because of the inductor will not allow the switches to immediately turn off or the current to change immediately, it will follow the input voltage until the inductor releases its energy. That concept you know. Okay, so the duration it has extended is called as extinction angle. Okay, so beta is the extinction angle here. Now what will be the output current, average output current? So that you can simply calculate by V naught average divided by R, because we have average inductor voltage equal to 0. Okay, then if suppose I have to calculate the power factor here, again we can use the same formula, RMS output voltage divided by the average V naught RMS upon Vs RMS. Okay, have I written the same thing here? Yes. Okay, and RMS value if you wish to calculate, you can calculate by using the trick formula. Okay, so by using that formula you can calculate the RMS value if it is required. If it is not required, no need to do such calculations. Okay, normally in rectifier we are very much interested in finding the average values. Okay, so all the average value formulas are very important for you. Now if suppose we have RLE load, okay, so if we have RLE load, there will be E as well. So what will be the firing angle? The firing angle should be in between theta 1 to pi minus theta 1, or sometimes we call it theta 2 as well. So this is the range of firing angle that we have to take. Okay, sir, B will come when freewheeling diode is not present. B will come, what B, Nilmesh? Beta will come when freewheeling diode is not present. Yes, of course, because if freewheeling diode is there, why we are using freewheeling diode? Because of that negative spike that we are getting. So we are trying to eliminate that negative spike, and that is the purpose of using the freewheeling diode. Okay, Nilmesh? Fine. Because if suppose negative spike will be there, what will happen? Due to the negative spike, there will be power transfer from load to source. So we need to eliminate that particular thing. Is that clear? So whenever we have we have inductive load, beta concept will be there, and freewheeling diode is just to eliminate that beta concept. Okay. So in RLE load, the firing angle should be in this range, and how to calculate this theta 1? This theta 1 is basically equals to sine inverse E over Vm. Okay, this is how we will calculate theta 1. Okay, now what will happen? So this should be the firing angle. Okay, and after that, yes, thyristor will be forward bias in what duration? If suppose we are, or what I can say, that E is greater than Vs or Vm sin omega t, I have to say. And when it will be show? When the omega t instant is less than theta 1, okay, or omega t instant is greater than pi minus theta 1, that then we will be having E greater than Vm sin omega t, and during that SCR will be reverse bias. Okay, SCR will be reverse biased through the E, the EMF of the battery, we can say. Now what will happen? We can calculate I naught current by this formula, Vm sin omega t minus E over R. Okay, then if I have to find the average value of it, what I have to do? 1 upon 2 pi, again we have L. So what will happen if suppose we are not using freewheeling diode? Beta concept will be there. Okay, and you will write this value, Vm sin omega t minus E upon R d omega t. Okay, so through this formula you can calculate the average value. And then whenever we have RLE load, one thing that you should know, that V naught average, this is equals to E plus I naught average into R. Okay, so this is the load side KVL whenever we have RLE load. Okay, so whenever we have RLE load, we will be using this formula at the load side for applying the load side KVL. Okay, so if we have R load or RL load with freewheeling diode, these are the important formulas. If we have RL load, these are the important formulas, and if we have RLE load, this becomes very important. Okay, so this is all about single phase half wave converters. Now let us discuss single phase full wave converter. So now pulse width will be pi. Okay, so time period will be pi right now. So when it comes to single phase full wave converter, so now you know what will happen in all the cases, all the loads. So I am considering RLE load. Okay, so what will happen here? Just see, during the positive cycle, when there will be a positive cycle and when there will be a negative cycle. Okay, so this is the reference direction for the source current. When we have negative cycle, the source current will be flowing like this. Okay, so during the positive cycle, what will happen? During the positive cycle, we have T1 and T2, they are forward bias, and when you will give them the gate pulse, they will start conducting. Okay, so at omega t equals to alpha, they are gated. Okay, and they conduct from omega t equals to alpha to pi plus alpha. T1 and T2 are on, and during that time your output voltage will be following the input voltage, and your output current will be following the source current. Okay, but during the negative cycle, what will happen? During the negative cycle, what will happen during the negative cycle? We will be having T3, T4, which are forward bias. Okay, now they are forward bias, so you will gate them at omega t equals to pi plus alpha. Okay, at omega t equals to pi plus alpha, they are just gated. So when you will gate them, they will conduct from omega t equals to pi plus alpha to 2 pi plus alpha, and when they will conduct, again your output voltage will be input volt equal to input voltage, but your source current and the load current, they are now opposite. Okay, so source current will be minus of I naught. Okay, so this is what will happen here when particular switch will be on. How will be the output voltage waveform? So let me just draw the output voltage waveform. So just see the output voltage waveform, it will be having this particular shape. Okay, so the output current waveform that it will follow this particular shape. Okay, where this is alpha, this is pi plus alpha, this instant is 2 pi and this is 2 pi plus alpha. Okay, now here what happened, here T1 and T2 has conducted, here T3 and T4 they have conducted. Again we will start conduction with T1 and T2. Now what about the current? So if we assume continuous conduction, the current will increase and decrease like this. Okay, so this is how your current will be varying. So this is the output voltage waveform and this is the output current waveform. So the waveforms will be like this. Okay. Now if we want to calculate the output voltage average value, so average output voltage, what it will be? Average output voltage will be Vm by 2 pi, sorry, twice Vm over pi cos alpha. That will be the average output voltage, and RMS output voltage has a particular formula here, so that you should know. This will be equals to Vm by root 2, or simply we can write Vs. Okay, so output, average output voltage and RMS output voltage will be having these formulas. So this is how the single phase full wave converter waveforms and formulas you will get. Now if we assume that L value is very high, so if suppose the circuit inductance is very high, so if L is very high, what will happen? If L value you are having very high, then your output current will become ripple free and constant like this. Okay, it will become ripple free and constant like this. Then what will be the source current? So if I am going to plot the source current will be having this particular shape. So just see about the source current. So if suppose I am calling this instant to be alpha, then if suppose I am calling this instant to be pi plus alpha, then I am calling this instance to be 2 pi plus alpha. Okay, and you know that from alpha to pi plus alpha, T1, T2 has conducted, and from pi plus alpha to 2 pi plus alpha, T3 and T4 has conducted. Okay, so how will be the output current? So source current is exactly equals to output current when T1 and T2 are on, isn't it? And source current is minus of output current when T3 and T4 has been on. So this is your output current. Now how will be the source current? Like this, just see. This will be the shape of your source current. So this is alpha, this is pi plus alpha, and this is 2 pi plus alpha. Now here you will be having 2 pi and here you will be having pi. Magnitudes will be I naught and minus of I naught. So this is the source current. Now if I talk about any thyristor current, how it will be? So just see, if suppose I am plotting thyristor current for T1 and T2. Okay, so just see, when T1, T2 are conducting, you will only get the current through them unless there will not be any current across T1 and T2. So this is how it is going to be the shape of current T1 and T2. Okay, so from alpha to pi plus alpha, out of this 2 pi you are getting thyristor current, okay, across any thyristor. So all these are the important waveforms regarding the current. Now just see how many things we will be able to calculate from here. So what is the output voltage RMS current? This is simply equals to the magnitude of I naught, isn't it? Now if I calculate the source current RMS value, so what will be the source current RMS value? Just see, source current is having a square wave waveform but some shifted value. So shifting does not affect the RMS value. So source current RMS value will be equals to I naught. If I calculate the thyristor current RMS value, then its magnitude is I naught, okay, and it is only present from alpha to pi plus alpha, that is for pi. So it is present for pi out of total available duration of 2 pi. Okay, so what I will get? I will get I naught upon root 2. That will be my thyristor current. Okay. Now if suppose I want to find out the Fourier series expression, so just see, your source current has to be a pure sinusoidal, but it is a square wave kind of waveform, isn't it? So we have to write the Fourier series for it because it is having harmonics. So the Fourier series expression will be n equals to 1, 3, 5 to infinite 4. What is the magnitude? I naught. So 4 I naught upon n pi. Okay. And for a perfect square wave, how you are writing the Fourier series? Sine n omega t, isn't it? But this one is a shifted one. So I will write here sine n omega t plus phi of n. Okay. Where what is phi of n? Phi of n is minus of n alpha. So this is going to be the Fourier series expression. Okay. This is going to be the Fourier series expression for the source current, harmonic expression for the source current. Okay. Now from here we can calculate so many things. What is the fundamental displacement factor, FDF? The fundamental displacement factor will be cos of phi 1 or cos of alpha. Okay. Then what will be the power factor? The power factor is current distortion factor into displacement factor. Okay. And what will be the current distortion factor? So the current distortion factor will be the fundamental RMS value divided by the total RMS value of the source current. When you will do that, you will get 2 root 2 over pi. Okay. Now just come here and put these values. So you will get 2 root 2 upon pi cos alpha, and this is the most important formula. So many times we have seen a gate question related to this. Okay. So just see, here it is. Every formula, important formula is written in front of you in this page. Okay. So all these are very, very important formula. Apart from this, what do we have? The average and RMS voltage expression. Okay. And one more important thing that you should understand, that load side KVL, this will be V naught equals to E plus I naught R. Okay. For alpha less than 90. Okay. So this will be your load side KVL. But the same expression will become V naught equals to minus E plus I naught R when alpha will be greater than 90. Okay, when alpha will be greater than 90. So when alpha is less than 90, as per this formula you will be getting a positive voltage. That's fine. Rectification operation is there. But alpha greater than 90, that formula will give you a negative voltage. Okay. So in that case you have to reverse the value of E. You have to reverse the polarity of E. So that now converters can operate as line commutated inverter, converting DC into AC. Okay. So this you should know. When you have to use plus E, when you have to use minus E, just look into the value of alpha. Okay. So this is related to single phase full wave converter. This is what we have. Now single phase semi converter. So if we have RLE load here, and if suppose we have used a freewheeling diode, then what will happen? This negative spike, if suppose you want to remove this negative spike, what you have to do? You just have to use a freewheeling diode and this negative spike will not be there, because during this moment freewheeling diode will be conducting. So in semi converter, exactly what we are doing? We are doing the same thing. Okay. So why they are called semi converter? Why they are called full wave converter? So just see here, if we talk about the output voltage and current, so there are two possible polarity of output voltage that we can get, but output current it is having only one polarity. So this is, we are getting a two quadrant operation here, isn't it? But here only one quadrant operation will be there. Okay, we will be having only first quadrant operation, no negative output voltage. We are only getting operation in the first quadrant. Okay, so they are called as semi converter. So in semi converters, what will happen? Now you may use both thyristors here, or this is diode, so this should not be there. Okay, or you may use all the thyristors. Okay, you may use all the thyristor and you may use freewheeling diode. Any combination is possible. You may use thyristor here. You may use diode here with no freewheeling diode. You may use all thyristors and freewheeling diode. You may use thyristor diode like that, okay, with no freewheeling diode, or you can use all thyristor with freewheeling diode, which we have used here. So if you are doing this, what will happen? From every, so earlier what has happened and now what will be the change? From pi plus alpha, from pi to pi plus alpha, okay, and from 2 pi to 2 pi plus alpha. Now who will be conducting? The freewheeling diode will conduct. Okay, now freewheeling diode will conduct, and no negative spike will be there. Okay, so what is the advantage of using freewheeling diode? No negative spike will be there, so no power transfer from load to the source will happen. Okay, so what will happen? Overall efficiency will increase. We are designing a rectifier which has to convert AC into DC, not a case in which DC is converted back to AC. Okay, so net power consumed by the load will increase if we are using freewheeling diode, so efficiency will be more, power factor will be more. This is the advantage. So semi converters are more advantageous than the full wave converter. Now how will be the output voltage waveform? So just see, the output voltage waveform will be like this. If this is suppose alpha, and if I am calling this to be pi, this will be pi plus alpha, and then if suppose this is 2 pi and this is 2 pi plus alpha, then how will be my output voltage? So my output voltage will now be having this shape. Okay, now just see, from pi to pi plus alpha I am not having any negative spike which was there earlier. Okay, so this is the change that we have created by using freewheeling diode. Okay, if I talk about the current will be varying like this for continuous conduction. So this is your output voltage and this is going to be the output current. So this is V0 and this is I0. Now who has conducted and when? So here we will be having T1 and D2 conducting. Okay, here we will be having freewheeling diode conducting. Okay, and let us suppose that I have used all the thyristors here. So let me call this T1, T2, and then this will be T1, this is T2, and this will be T3, and this will be T4. Okay, so as per this, what will happen? Here I will be having T1, T2 conducting, then freewheeling diode will conduct. Then I will be having T3, T4 conducting, and then I will be having freewheeling diode conducting. So this is how the conduction will be there. Sir, book कहाँ मिलेगा? Which book are you talking about? कौन सा book का बात कर रहे हो राजू? If you want to purchase IMS Gate Academy books, you have to enroll with us and then you can purchase our material. Okay, so there is a description link given in the box, so from there you can join our Telegram channel. Okay, and there you can ask us or you can just contact us. I will be sharing the details. You can contact us and there you will be getting all the materials. Okay, if we use the diode, thyristor diode combination, we have to use freewheeling diode. No, Nilmesh, in that case you don't have to. Okay, I discussed that. Freewheeling diode you will not be using if you are using thyristor IMS Gate Academy का book लेने के लिए you have to enroll with us. Okay, I will be sharing the contact details, so you have to contact on those details, or the description box has the Telegram group channel link, so you can just join our group and all the information will be available there. Okay, just call on the numbers and you will get all the information how you can purchase the books, the theory book, exercise book and gate question bank. Okay Raju, is that fine? The description box has all the information. From there you will get the numbers. You can join our Telegram group channel as well. Okay, and then you can purchase our material. Now just see. So this will be the waveform. Now if we will calculate the average voltage, okay, so V naught average, what it will be? Now V naught average will be Vm by pi 1 plus cos alpha. Okay, and RMS value. सर SCR एंड डायोड का वेव फॉर्म कैसे बनाएंगे? SCR एंड डायोड का वेव फॉर्म कैसे बनाएंगे? SCR और डायोड करंट का अभी आ रहा है उस पे, ठीक है, बनाते हैं अभी, जस्ट वेट. So RMS voltage you can calculate by using the formula. Okay, so what we have actually done here, time period will be pi and we have integrated from alpha to pi Vm sin omega t d omega t. Okay, so that's how you can find out the average output voltage here. Okay, now let us talk about the currents and the expression, and assuming that the L value is very high. So what will happen if the L value is very high? The output current can be assumed to be constant. Okay, so output current will be constant. Okay, and Raju, just go to our playlist. In that playlist you will find fundamental series lectures of power electronics. There I have covered almost 10 important topics of power electronics. So just go to those lectures. We have discussed in details each and every bit of these topics. Okay, this is the revision lecture, so I have to be very limited. If I cannot do proper detailing of everything, okay, unless the purpose of this lecture will not be served. So I will post after this lecture the link of that fundamental series, so you can just go into that series and you can watch all the lectures in which all the details, small to small bit, has been covered there. Okay, so you will get the fundamental clarity about everything. Fine. So come here, this is output current I naught, which is constant. Now let us plot the source current. So if I talk about the source current, now tell me, whenever freewheeling diode will be conducting, well, whether any source current will be flowing? No. Okay, when the freewheeling diode will be conducting, none of the thyristors will be conducting, so source current will not be flowing. Okay, source current will be flowing when T1, T2 and T3, T4 are conducting. So let this be alpha and this be pi plus alpha, and this to be 2 pi, then this is 2 pi plus alpha. Okay, so what has happened? During this movement we have T1, T2 conducting. During this movement we have freewheeling diode conducting. In this movement we have T3, T4 conducting. Again back here we have freewheeling diode conducting. Okay, and here also we have FD. So as per this, if I draw the source current will be flowing from alpha to pi through T1 and T2. When freewheeling diode is conducting, there will not be any source current. When T3, T4 will be conducting, again source current will be flowing and it will be having negative value. Okay, because in the negative cycle it is flowing equal to I naught, the value it will be having. So just see, this will be the waveform. Okay, so it is alpha, this is pi plus alpha, and this is 2 pi, and this is 2 pi plus alpha. Okay, is that clear? Raju, did you get the clarity? Regarding purchasing the material, the link is given in the description box, the numbers are given there, you can call and purchase. And regarding the fundamental series, where I have covered all these topics in very detail, I will post the link after the class. Okay, so you can just go through that particular link and attend all those lectures, and fundamental clarity will be there with you. So this is I naught. Now let us plot the thyristor current. So if I talk about the thyristor current, so let us take an example of T1 thyristor current across T1 T2, and it will be like this. Just see, T1 and T2 are conducting only from alpha to pi, and they are not at all conducting anywhere else. Okay, so from alpha to pi they are only conducting, and at that time the current is I naught. Then if suppose I plot the freewheeling diode current, okay, so if I just plot the freewheeling diode current, so you can see freewheeling diode is conducting for every pi to pi plus alpha. Okay, so from every pi to pi plus alpha we will be having freewheeling diode current. Okay, just see, from every pi to pi plus alpha or 2 pi to pi plus alpha we will be having freewheeling diode current. So let me call this pi, and this is pi plus alpha. Okay, this is 2 pi and this is 2 pi plus alpha. Magnitude is I naught. This is the freewheeling diode current. So just see, we have just plotted all the waveforms here. Okay, so if we talk about the respective values of the current, so if suppose I want to calculate the RMS value of source current, what it will be? So the RMS value of source current, the magnitude is I naught, and this is present from alpha to pi. Okay, so pi minus alpha, and what is the cyclicity? The period is pi. Okay, so this is how you will get the RMS value of source current. Now when it comes to thyristor current, so just see, thyristor current RMS value, what it will be? The magnitude is I naught, and this current is present from alpha to pi, so it will be pi minus alpha again, but from 2 pi cycle, just see, from the 2 pi time period we are getting only for alpha to pi, so time period will be 2 pi, so you will write here 2 pi to the power 1 by 2. When it comes to freewheeling diode current, so freewheeling diode current is present in every half cycle. Just see, it is present in every half cycle, and what is the duration for it which it is present? Only for alpha, so it will be alpha, and since it is present in every half cycle you will write pi here, so I naught alpha upon pi to the power 1 by 2, that will be the freewheeling diode RMS value. Okay, now after that, if suppose I have to write the Fourier series expression, okay, so what will be the Fourier series expression for the source current? So just see, the source current is having a quasi square wave kind of waveform, but not a perfect quasi square wave. We have to shift it by alpha by 2, and then it will become a perfect quasi square wave. So we are shifting by alpha by 2, so n value will be 135 to infinite, magnitude is 4 I naught upon n pi. Because we are shifting by alpha by 2, so theta will become alpha by 2, so cos n theta or cos n alpha by 2 we will write here, and sin n omega t plus phi n because of the shifting. Okay, where what is the value of phi of n? This is minus of n alpha by 2. So this is very important expression. So many times there has been a gate question upon this expression. Calculate the fifth harmonic, third harmonic, fundamental harmonic RMS current of semi converter. So you should know this expression. Okay, then what is the FDF? Fundamental displacement factor, it will be cos of alpha by 2. Okay, and then rest of the calculation you can do. For example, if you have to calculate the power factor, you will be calculating the current distortion factor into the displacement factor. I am not doing all those things because we don't have any fancy expression when it comes to semi converter. Okay, so you can do all those calculations. So this is all about the freewheeling, the semi converter. This is the average output voltage expression, which is very important. All the current expressions are very important. They may be asked in the exam. This Fourier series expression is also very important. It might be asked in the exam. Fine. So this is about the 2-pulse converter. Coming into the 3-pulse converter, 3-phase half wave converter. So in three-phase half-wave converter, we have two possible combination. Just see, in this combination, all the cathodes are connected together. So it will be called as common cathode connection. Okay, and here all the anodes are connected together, so we will call it common anode connection. Common cathode, common anode connection. Now in common cathode connection, just see, any thyristor, it will conduct whenever the respective voltage is going positive maximum, isn't it? T1 will conduct when VAN is going positive maximum. T2 will conduct when VBN is going positive maximum. So when common cathode connection is there, your output voltage will be always positive, isn't it? Now just see here in common cathode connection, any thyristor will conduct if the respective phase voltage will go negative maximum, isn't it? So here your output voltage will always be tracing the negative portion of the waveform, isn't it? Now, what are the important formulas? So here we have when alpha is less than 30, okay? So if alpha is less than 30, the average output voltage formula, this will be 3 VML over 2 pi, or sometimes you will see 3 root 3 VMP is also written, okay? So 3 VML upon 2 pi cos alpha, okay? And this formula is valid for R load for alpha less than 30, okay, and for RL or RLE load for any alpha, okay, for any alpha. So this is going to be the output voltage formula. What will be the pulse width of each pulse? The pulse width here will be 3 pulse converter, means 2 pi by 3 or 120 degree, okay. Now when we have alpha greater than 30, in that case what will be the formula? In that case the formula will become V naught average, that will be 3 VML upon 2 pi, we will write here 1 plus cos alpha plus 30, okay, and this formula is valid for R load when alpha is greater than 30 and RL or RL load plus freewheeling diode, okay, or RLE load plus freewheeling diode. So just see, we have these two important formulas here. Average output voltage you will be calculating by using these formula depending upon the value of alpha, okay. So these are the two important formulas that you have for three-phase half-wave converter. Now when it comes to three-phase full-wave converter, just see, common cathode and common anode, they are connected together. So here what voltage you will get? You will get a voltage here Vx, let us suppose one voltage you will get here V of y. So output voltage will be what? The output voltage will be Vx minus Vi, which will give you always a positive value, okay, which will always give you a positive value. So what will happen here? You will get, what will be the pulse width? The pulse width here will be 2 pi over m or 2 pi over 6 or pi by 3 or 60 degree, okay. So you will be getting 6 cycles of output voltage for a complete 360 cycle of input voltage, okay. So this is going to be the pulse width. Now what will be the output voltage? So when you have alpha value less than 60, so if alpha is less than 60, we will have the output voltage, average output voltage, this will be equals to 3 VML over pi cos of alpha, okay, 3 VML over pi cos of alpha, and this expression is valid for R load, okay, or RL load or RL or E load for any value of alpha. For R load it is valid for when alpha is less than 60, okay. This is how you will get it. Now if suppose in this case I plot the source current, which is very important here. So let me just plot the source current. So just see, if I am going to plot the source current, what I will get, okay, assuming very high inductive load. So source current, if I plot source current, each pulse width is 60 degree, okay, and here one more thing you will get, each switch will conduct for 2 pi by 3 or 120 degree, okay. So if I am talking about source current, so what will happen, just see, source current will enter, if suppose entering from T1, then it will return back from T4, okay. So T1 will conduct for 2 pi by 3, T4 also conduct for 2 pi by 3. When T1 is conducting, source current is getting in, when T4 is conducting, it is getting out. So for T1 it will be positive and for T4 it will be negative. So if we just plot this current, what I will be getting is this kind of shape, assuming high inductive load, okay. So this will be 60 and 180, then we will be having 240 to 360. Okay, and the magnitude, it will be I naught. Just see, this is how we will be getting the source current waveform. Okay, so this will be my source current waveform. Now if I have to plot the thyristor current waveform, just see how will be my thyristor current waveform. So let us plot for any thyristor. If suppose I am plotting it for thyristor T1, okay. So if I plot for thyristor T1, just see, here we have T1 conducting, here we have T4 conducting. So if I plot it for T1, just see what will happen. I will get this kind of waveform. Okay, so this is what 60 and this is what 180, and here I will be having 2 pi or 360. The magnitude will be I naught. Okay, so if I have to calculate that what will be my source current RMS value, then it will be I naught, or let me use more space. So looking into this source current waveform, if I calculate what will be my source current RMS value, so just see, magnitude is I naught and my source current is present for this 120 duration. Okay, so what I will do, I will write 2 pi by 3 or 120 upon pi, or what I will get I naught under root 2 by 3. Okay, it is having a quasi square wave kind of shape. So the way we have to calculate the RMS value of quasi square wave, the same thing we are doing here. Now if suppose I have to calculate what will be my RMS value of thyristor current, just see, the magnitude is I naught and it is present for 2 pi by 3 duration out of total 2 pi available for it. Okay, so it is present for 2 pi by 3 duration out of total 2 pi available for it. So what you will get I naught upon under root 3. Okay, now if I have to write the source current Fourier series, then it will be n equals to 6k plus minus 1. Okay, so all the even plus triplen harmonics are absent here. Okay, now 4, what is the magnitude? Just see the waveform, the magnitude is I naught, okay, upon n pi. And is it a perfect quasi square wave that we have? No, we have to shift it. How much we will be shifting? This waveform we have to shift by 30 degree, pi by 6. Okay, so we are shifting this waveform by pi by 6. So what I will write here, cos of n pi by 6 sine of n omega t. Okay, n omega t, and how much we are shifting here? Instead of Yes, it is right. So let me write here n omega t plus n pi by 6. Okay, this is how I will be writing this source current Fourier series expression. This will be the source current Fourier series expression here. Then what do we calculate here? Current distortion factor. Okay, so current distortion factor here is 3 upon pi. Then power factor, current distortion factor into fundamental displacement factor. Okay, so what you will get? You will get 3 upon pi cos of alpha here. Okay, cos of alpha. Let me just write this to be phi n here. So you may write it phi n, or otherwise just let it be like this. Okay, so power factor here will be 3 by pi cos alpha, which is a very important expression here. Okay, which is a very important expression. We have this waveform, isn't it, Nilmesh? Now this waveform is not a perfect quasi square waveform. Just see what we have done in case of single phase full wave converter. Okay, this was the case. So in this, not this one, just this one. So just see this case, what we have done here. Okay, what we have done here. So this is not a perfect quasi square wave, we have shifted it by alpha by 2. Okay, so same way what you are getting here is you have to shift it by 60 degree, you have to shift it by pi by 3 here, pi by 6, isn't it? This waveform I have drawn assuming that alpha value is 0. Okay, this waveform I have drawn for a perfect diode assuming that alpha value is 0. So this is not a quasi square wave, you have to shift it towards the left side, left side. How much you will be shifting to make it a perfect quasi square wave? Pi by 6, isn't it? 30 degree. So this is how you will be writing here, 4 I naught upon n pi cos n pi by 6. Okay, and since you are shifting it, so you have to write it. Acha, you are saying minus. Yes, this is correct. Here it will be minus, not plus. Okay, yes, this will be minus. That's right. Okay, I was thinking that you are asking how it has been done. Now fine, Naru, Nilmesh. Okay, so power factor, which is 3 by pi cos alpha, is a very important formula. In single phase full wave rectifier we have a formula 2 root 2 upon pi cos alpha. In 3 phase full wave rectifier we have formula 3 by pi cos alpha, which is again very important here. Okay, I hope this is clear to everyone. Nilmesh, your doubt is clear? Is that fine right now? Okay, so all these are important formulas related to 3 phase full wave converter. The average voltage formula. Okay, now alpha less than 60 we have written. If suppose we have alpha greater than 60, in that case what will happen? So if you have alpha greater than 60, then your formula V naught average, that will become 3 VML upon pi 1 plus cos alpha plus 60. Okay, now that will be the formula. Okay, very good. So this is about 3 phase converters. Now let us discuss the effect of source inductance. Okay, in single phase full wave rectifier we have a formula 2 root 2 upon pi cos alpha for power factor. In 3 phase rectifier we have a formula 3 by pi cos alpha. Both these formulas are very important. Anyone can be asked. Okay, you will definitely get a question from these two formulas. Fine. Now the last topic, which is effect of source inductance. So till now we have assumed that there is no source impedance. If source impedance is having resistance only, it will only create a drop. But if suppose the source inductance is having some inductance, it will not allow the transition of source current suddenly. Okay, so what will be the effect? The conceptual clarity you can get from the fundamental series. I have covered this particular topic, okay, in which each and every detail has been discussed. Now we will discuss the effect of source inductance here. So what is the effect of source inductance? There will be a net reduction in the output voltage. Okay, there will be a net reduction in output voltage. Okay, and what is that net reduction? And we will discuss that, and concept of overlap angle will be there. Okay, so there is something called as overlap angle which is mu, and during this angle all the switches are conducting. Okay, all switches are conducting, and because of that we will be having output voltage equals to 0. Okay, so net reduction in the output voltage, overlap angle concept will be there, and all switches will be conducting. Okay, so if we talk about different converters, for example, if suppose we have single pulse converter, or if suppose we have 2 pulse converter, or if suppose we have 6 pulse converter, then what will happen? So V naught average old, then the reduction, okay, del V naught, and then what will be the expression for I naught average. If we discuss these 3 parameters, okay, so V naught old, and what will be the reduction, and then the average output current. So what will be the formula of this in all these 3 cases? Okay, let me use another page, so we will get more space. So if suppose we have single pulse converter, or we have 2 pulse converter, or we have 3 pulse converter, okay, so we will be having output voltage, old output voltage. For example, we have here 2 pulse converter. So in 2 pulse converter, what is the output voltage expression? It is 2 Vm by pi cos alpha. Okay, then the new voltage, okay, the new voltage will be the old voltage minus the reduction factor. Okay, so we will be having 2 Vm by pi cos alpha minus the reduction factor will be 4f ls I naught, where ls is the value of the source inductance. Okay, then we will be having the expression for output current, which will be Vm by 2 omega ls cos of alpha minus cos of alpha plus mu. Okay, so just see what we have followed here. The old voltage formula for every converter, we know that. Then we should know about how much reduction this source inductance is causing. Okay, because during the overlap angle all the switches are conducting, so output voltage is 0 during that duration, so there will be a reduction in the output voltage. What is that reduction? In 2 pulse converter it is 4f ls I naught. Okay, so what we will do, we will just subtract this reduction from the old voltage, and then we will get the new voltage, and then we have an expression for the current. Okay, Vm by 2 omega ls cos alpha minus cos alpha plus mu. These 3 are the important formula that you should know for this topic. Okay, so if I compare every converter here, okay, single pulse, 2 pulse and 6 pulse, then what will be the values of these things? So first of all, let me write V naught old for each case. Okay, so let us consider single pulse, and if I am considering R load or RL plus freewheeling diode load, okay, any example I can take. So I am taking R or RL load with freewheeling diode. Okay, now what will be the formula here? We have already written that 2 Vm by pi cos alpha. What will be the formula here? Here we will be having 3 VML upon pi cos alpha. Now what will be the reduction? Okay, so reduction here will be f ls I naught. Reduction here will be 4 f ls I naught. The reduction here will be 6 f ls I naught. Okay, sir, what will be current expression in 3 pulse converter? Same, Vm by 2 omega ls. Okay, current expression will be here only in single pulse converter it is Vm by omega ls only. Okay, just see Nilmesh, Vm by omega ls cos alpha minus cos alpha plus mu. Everywhere else it will be Vm by 2 omega ls cos alpha minus cos alpha plus mu. Here also we will be getting Vm by 2 omega ls cos alpha minus cos alpha plus mu. Okay. Now just see, if you know what is old voltage, you know the reduction factor, you can calculate the new voltage. Okay, and this is the expression for I naught. For 2 pulse, single pulse we have Vm by omega ls, everywhere else we have 2 omega ls. Okay, so just see, in this formula if you see, alpha is coming, and in this formula we have alpha plus mu, so mu concept is coming here. Okay, so mu, if suppose it is asked, you need the value of I, you need the value of I naught. Okay, one more important thing, without ls or with ls, there will be one more change. Okay, let me take an example of 2 pulse converter or 1 pulse converter. For example, if suppose I am talking about 1 pulse converter or 2 pulse converter. Okay, so without ls, each switch will conduct for maximum of 180 duration, isn't it? If suppose we have diode 180, if suppose we have thyristor 180 minus alpha, isn't it? This is the duration for which they conduct, and it depends upon load as well. If suppose load is RL, it is conducting from alpha to pi plus alpha, means 180. Okay, so in a general case, if I am talking about, and in 3-phase converters, switch conducts for 2 pi by 3, 120 degree, isn't it? But with ls, what will happen? This duration will be 180 plus mu in single phase. Okay, and it will be 2 pi by 3 plus mu in 3 phase. Okay, so if ls, you are encountering the effect of ls, there will be an extra mu duration added in the conduction period. This is what I am trying to say. Okay, so that extra mu duration will be added in the total conduction period. Okay, and guys, these formulas are very important. If you know the formula, there will be a very easy question on this topic and you will be able to solve that. Okay, so this is, I think, how we have completed single phase, we have completed rectifiers. Okay, so this is how the complete revision of power electronics is being done. Part 1, part 2, part 3 and part 4 are available. I think I have not taken more than 1 hour in any of the lectures. So total duration of this revision is only 4 hours, and these 4 hours you will be able to revise all important formulas of power electronics. Okay, so just have the revision, just have a look over these 4 lectures to revise the power electronics. Okay, apart from that, I will just post the link of the fundamental concept series. So in which what you can do, fundamental concept series is there, important concept series is there. So I will just post the link of those lectures after the lecture in the comment box. You can just go through. Okay, you can just go through all those lectures. If suppose you are left out with any of the topics, or if suppose you are thinking that you are not well prepared for power electronics, after going through those lectures, you will be able to do that. Okay, those are hardly there is any lecture of more than 1.5 hours. So you can just spend one complete day and you can prepare power electronics very well. Okay, and if you are liking the teaching and learning methodologies of IMS Gate Academy, just join IMS Gate Academy live online program. We are offering 800 live plus 800 plus hours of live teaching. We are offering you some exceptional content in terms of theory book, exercise book and gate question bank. We are also offering mentorship sessions. Okay, so the description is given in the, so the link, all the links are, and important information is given in the description box. You can join our Telegram channel, the link is there present. Okay, so that you may regular get the PDF of all the lectures. Apart from that, if suppose there is some government notification or some webinar, seminar we are creating, we will also notify you in that particular group, okay. And you can also purchase our content by writing in the group, okay. So I think the lecture served its purpose. Thank you so much for attending. Thank you so much.